Okay, let's go ahead and get started. Welcome to week 8 of the quarter, so we're almost there. So in today's lecture, we're going to be continuing our discussion of k-means clustering and unsupervised learning. As always, a couple of announcements. Fourth homework is due Friday. So in this homework, you're going to be implementing and also experimenting with decision trees. So make sure you check that out soon. And also the projects are coming up sooner rather than later. So they're actually due in just 3 weeks. So Monday of finals week is when your final submission for those projects are due. So highly recommend you guys get started working on those quite soon. Not this week, but next week's discussion section is going to be a project workshop. So it's a really good idea to have made fairly significant progress on your projects by Thursday of week 9. That way you can actually, make use of this resource, use the TAs during these discussion sections to get some help on your projects. And actually, before we get started with sort of the main content of today's lecture, we're going to go through some more details about the projects, hopefully give you guys some ideas of things you can do. There is that project page up on Canvas that has pretty much all the information, but I figured we could talk about it in class in case you guys have any questions. So yeah, we'll talk about the projects, and then we'll wrap up our discussion of k-means today. Okay, so by now pretty much everyone has gotten into project groups. I think I sent out grades for that. If you didn't get a grade for your project group, then you'll be assigned a group. And hopefully by now you've again all chosen your data sets. So we've got this diabetes medical data set, which is a tabular data set. We've got 2 image classification data sets. We've got a text classification data set here. Really, my goals for you guys in these course projects are just to see what it's like to apply machine learning techniques to sort of real-world, quite realistic data set. So really here, your goal is to gain insight about your models, gain insight about your data sets, and really see a machine learning project through start to finish. The goal is not necessarily to build the world's most accurate classifier for your data set. So I don't want you to spend hundreds and hundreds of hours trying to get that extra 0.2% accuracy with your models. So really the goal is less about very high performance and more about insight and understanding. So kind of start to finish, what you should do in your projects, what's expected of you, is that you should understand your data set in full detail. So you should really, really understand the data set you're working with before you start doing any analysis on it. So you should do things like exploratory data analysis, where you visualize your features, plot your data, these kinds of things. So we did this in the very first week of class, lectures 1 and 2, so you can use some of those techniques that we talked about there. You're required then to evaluate at least 4 different classification models on your chosen data set, 3 of which should be KNN, logistic regression, and a feed-forward neural network. And then your 4th model can be something that you choose. So one of the models we talked about in class, or potentially something a bit more complex. If you're working with some of these image data sets or the text data set, then you might try out some models that we didn't talk about in class, at least not necessarily in full gory detail. So something like a convolutional neural network on images might be a good choice if you're working with, say, the CFAR10 data set. In fact, you're probably not going to get very good performance on that data set unless you use a CNN, so I would definitely look into using those. There's also models that are called recurrent neural network, which are really good for text data. We didn't go into details in those in class, but you can do some digging on your own and figure out how to use those. So we did introduce you guys to PyTorch in last week's discussion section. So if you're interested in using these more complex neural network models on your data sets, that PyTorch tutorial, also available on the Canvas page, is going to be really helpful. And you should try to get the best possible performance out of each model through hyperparameter tuning and really experimenting with the models. That's not to say you should, like I said, spend hours and hours doing hyperparameter tuning, but you should put in a good faith effort to get pretty decent results. You don't want to just use the default settings provided by scikit-learn and say, okay, this is what my model does. So you should really play around with these and try and figure out, how they work, how you can get them to work better. And again, most importantly here in the projects, I want you to be able to derive insights about both your model and your data set from various experiments that you will run. So, for example, what I mean by insights about your data and data sets are, maybe are there particular classes in my data set or particular data points that are very hard to classify? Maybe my model does really good on everything except for the cars for some reason. And if you find that this is the case, maybe particular classes or data points are misclassified by every model you try to come up with an explanation for that. Why would this be happening? Generate some hypotheses about that and maybe test them. You might also ask something like, are certain types of models better on my data set than others? And again, you shouldn't just ask these questions and say yes or no. You should try and provide some justification, some why. Why is KNN doing so much better than a logistic model here, for example? You might also ask, what are the limitations of the models? Maybe I tried out 4 different models and got pretty bad accuracy with all of them. Why would this be happening? Could we come up with some kind of explanation? You can go even further than that and think, okay, how might I overcome the limitations of my models on these data sets? Maybe propose some kind of fix. Overall, I want you guys to try and be creative with these projects. So really try to ask and answer questions about your data and using your data. So some more ideas, sort of more creative things you can do in these projects. Rather than looking at just classification accuracy to evaluate your models, you might look at confusion matrices. We introduced those a few weeks ago. You could also look at other metrics like precision and recall. There's a whole host of other metrics you can use for classification, like F1 scores and AUC scores. So you can do a little bit of research of those on your own, plenty of resources online, and maybe report these numbers as well. You can also do like an error analysis, really dig into the errors that the models are making. You could do something like looking at learning curves. And what I mean by a learning curve is on the y-axis of a plot, we have, say, the error rate of a model, and on the x-axis, I have the number of training data points. So in essence, you can get a sense of how models scale with dataset sizes. And in doing so, you can compare different classifiers based on how much available data you might have. Neural networks aren't going to do great if you have a tiny data set, and you can kind of prove this experimentally on your projects. You might do something like investigate the complexity error trade-offs of your various models. So we've seen plots like this over and over again in the course, where on the x-axis we have some measure of model complexity, like the number of parameters in a neural network, and on the y-axis we have error on a training and test set. And you might try and reproduce those sort of U-shaped curves we saw, where we essentially overfit or underfit our model. These are actually harder to create than you might think, so you might need to play around with, say, the training set size and different model parameters to actually reproduce these kinds of graphs. Another interesting thing you might check out is model interpretability. So by interpretability, I mean, okay, I have some big black box machine learning model. How can I understand why it's making the predictions that it's making? So you might, in some sense, investigate what features the model is relying on in order to make its predictions. One really simple way of doing this is just remove features one by one, train a new model on all of your data except that one feature, and measure how much the accuracy increases or decreases. So essentially, how important is this particular feature? We can test this by training with or without that feature. For something like a neural network, we showed a couple of plots, actually visualizing the hidden units before. You could, produce graphs like that and try and understand what each hidden unit is doing. In addition, there's a bunch of visualization and kind of cool interpretability tools out there for neural networks. So you could do some digging and some research about those and maybe include some of those techniques in your report. So overall, pretty open-ended. And again, the idea is insights about your models and insights about your data. Okay, there's a couple of frequently asked questions that we've gotten so far regarding the projects. So I figured I would go through these real quick for the sake of the whole group. The first question is, how do you actually handle categorical features? So we saw in something like a decision tree, well, these models just naturally handle categorical data. We don't need to do anything for those. But if we have categorical data and we want to, say, apply that to a logistic regression model, we're going to need to do some kind of encoding of that data. And the idea here is we're going to somehow represent our categories appearing in our data in some kind of numerical fashion. And then once we have numerical feature vectors, we can just plug them into the model as if they were any other numerical feature. So really there's 3 basic ways of doing this kind of encoding of categorical features. The first is called a binary encoding. This is when you have some feature in your data set that only takes on 2 different values. So maybe you have some kind of loan application data set where someone comes in, one of their features is whether or not they're currently employed, so it might be encoded in your data set when you download it as either a yes or a no. And the simplest way to turn this into a numerical feature is just say map yes to 0 and turn all the no's to 1s. So we turn these binary categories into a 0-1 feature vector, and this is kind of the simplest thing you can do. Another notion of encoding is called ordinal encoding. And this is where you have a categorical feature that has some natural ordering to it. So maybe we're looking at income, and maybe this takes the values low, medium, or high in your data set. And in this sense, it might make sense to map all the lows to zeros, all the mediums to ones, and all the highs to twos. And this really only makes sense when you have categories that have some natural ordering to them, because we're encoding them in integers that are, in increasing order here. You would not want to do ordinal encoding if you have just categories that aren't really sorted in any kind of meaningful way. So you might have some kind of variable representing what state a person lives in. It might be encoded in your original data set as just a 2-letter code, so AK for Alaska, AZ for Arizona, all the way up to Wyoming. And what we can do for these is create a new binary feature for every possible category. What I mean by that is I'll make a new feature called state AK, I'll make a new feature state AZ, so on and so forth, all the way up to state Wyoming. So I make 50 new features for this particular categorical variable. Then if a particular data point comes on, and say this person lives in the state Wyoming, well, I have zeros for all 49 of my first states, so they don't live in Alaska, they don't live in Arizona, but they do live in Wyoming. So in this way, I can take a categorical variable and encode it as a sort of sequence of binary variables. So in all of these, again, the basic idea is we take some categorical feature and represent it numerically. Okay, it's kind of a pain to do this by hand. Imagine trying to create 50 new features for that state variable. So if you're trying to do categorical encoding in your data sets, there's this nice Python package called pandas that has a tool that will do this for you called get dummies. So check out the documentation for this. It's very useful. Okay, another question we've gotten a few times is, what's a good enough error rate on my data set? How do I know when I'm done tuning my model? And the answer, this is probably the answer you don't want to hear, is it depends. Some data sets are just inherently more difficult to get high accuracy on. Imagine a very high dimensional image data set versus something like that penguins data set. So sort of a priori, when you don't know anything about your data set, you just have some data and are trying to fit models to it, well, the only way to figure out what a good accuracy is to fit a bunch of models and put a good faith effort into tuning those models and trying to really get the best performance that you can. So there is no real sort of baseline error rate here that we're targeting for. We're just trying to get the most out of our tools that we have available to us. And again, just emphasizing, the goal of the project is not to get state-of-the-art accuracy on these data sets. It's really about insights and understanding both the models and the data sets. Okay, and then the last question we've got here is, how do you actually handle missing data? So in the real world, when you have an actual data set, most of the time it's going to be a very messy data set. People drop out of studies all the time and maybe have some features missing for them. Maybe a patient comes into the hospital and didn't get their blood pressure checked for some reason. So data in the real world is very, very messy. Oftentimes, this messiness shows up as missing data. So in the penguins data set, we might have some rows that have nans for not a numbers, meaning that some features about this penguin was not measured. And the simplest way you can handle missing data in your data set is just drop the rows that have any degree of missingness to them. Maybe this first penguin, I measured everything except for their bill length. Well, I could just drop that penguin. This is really a very simple thing to do. And in practice, people often do this because it is so simple and so easy. But it's not ideal because you're just throwing away data that you might have gone out and collected. So you might try a technique here called imputation. And the idea behind imputation is you try and fill in these missing values based on the rest of your data set. So maybe if I was missing the bill length for this first penguin, I could say, okay, maybe let me take the average of all the other bill lengths and then put in that average bill length for this feature that's missing. That's a really simple imputation technique, just taking averages, but there's lots more out there. And so if you're interested in exploring this could be one of those kind of additional creative things you do for the project, is trying to fill in missing data and evaluating the various techniques. And there's lots of resources online, again, about how to do data imputation. In any case, if you work on one of these data sets that has missing data, particularly the diabetes data set, make sure you at least write in your report what you choose to do to handle this missingness, and at least have some kind of justification of why you chose to handle the missingness in this way. Okay, any questions about projects? Yeah. Yeah, I mean, feel free to do that for the project if you're interested in exploring something like that. I'm not sure how well it's going to work for something like the diabetes data set, but try it. Let me know how it goes. Yeah. Mm-hmm. I forget exactly what error rates you're going to get with like logistic models on Sci-Fi, but it's not very good. With like a CNN, you can get like high 90s in the accuracy for that data set, and with a logistic model, I'm not going to make up a number, but it's pretty low. In any case, that's okay, as long as you can come up with some reason why logistic models aren't good enough there, for example. Yeah. Other questions on the projects? Yeah. Yeah, you should do a pretty thorough exploration of your models in the sense that you should, put a decent amount of effort into tuning them and getting decent performance. But there's no, like, if you don't get X error rate, you're going to lose 10% on your project or something like this. As long as you do a good job exploring the models, then you're good to go. Yeah, if you're getting an error rate of 99%, then yeah, you're probably doing something wrong. Keep in mind that there's this notion of the majority classifier that we introduced a while ago, right? Where you just predict the most frequent label in your data set. So unlike Sci-Fi 10 with 10 classes, if you're getting an error rate that's, say, worse than 90%, well, you're doing worse than just randomly guessing, basically. So there are simple baselines like that can kind of sanity check your performance. But yeah, there's no like necessarily particular target you're reaching for in the project. Yeah. Okay. Yeah, if there's further questions, which I'm sure there will be as you actually start working on these, please do post them on Ed, and keep in mind we'll have that project workshop next week. Okay, so let's start the actual machine learning portion of today's lecture. And so we'll be going through kMeans today and going through some more details here. So just a reminder of what kMeans is and what our goal is here. So far, in regression and classification problems, these are all supervised learning problems, where in our data set, we're provided some target values that we're trying to predict from the original features. In contrast, in unsupervised learning, which is what we're looking at now, we don't have any target values associated with our data. We just have some big unlabeled data set, and we'd like to somehow automatically extract insights or understand this data. So a classic example of a task here is clustering. So let's say I went out and collected some data, created a scatter plot of it, and visually you can see, very intuitively, there's two groups of data here. And I'd like to somehow be able to extract these two groups of data into two different clusters. I can, of course, just randomly assign labels, but this is, not going to do a very good job. I'm going to have some bad clustering. And ideally what I want is to, separate these two clusters automatically. So just a reminder on notation. My data set now is just a big data matrix X, and there's no associated vector of labels Y. I'm going to use Z's to denote cluster assignments. So Z sub I is the cluster assignment of a vector X sub I. So to every data point, I'm assigning some cluster label. And these cluster labels come from the set 1 through capital K. So I can have capital K different clusters. Here, capital K, the number of clusters that I'm fitting to the data, is a hyperparameter of the model, so I need to choose this before I fit the actual clusters. And after I cluster my data, I'm again assigning a cluster label to every single data point. Each cluster itself is going to be represented by a centroid, where a centroid is just some d-dimensional vector. So my features are d-dimensional, my clusters are also just d-dimensional vectors. It's essentially some point in my data space representing the center of the kth cluster. Okay, so if I have cluster assignments for my data points, so I know for every data point what cluster it lives in, I can compute the centroid of that cluster by just taking the mean of all the data points that live in that cluster. So again, centroid of a cluster is just the average of all the data points in that kind of cloud of points. And we also introduced ourselves to this really simple clustering algorithm called kMeans, where in kMeans what we do is we first randomly initialize our clusters, so again the sort of centroids of each of our blobs of data. We're going to initialize them as just randomly selected data points. And there's only two steps in this algorithm that we iterate between until convergence. The first is we assume that we're given the cluster centroids, and given those cluster centroids, we assign a cluster label to every data point. In step 2, we kind of flip things around. We assume that we're given cluster assignments, which are the ones we computed in step 1. And what we do then is we then compute or update the cluster centroids. So we alternate between assigning cluster labels and updating those centroids. This algorithm is guaranteed to converge. We'll see some more details of that later. Okay, let's step through an example, kind of slowly, of how this kMeans algorithm actually works. So this is the same data set I showed you guys before. At initialization, before I do anything at all, I'm just going to randomly select 2 of my data points here, and these are going to be my cluster centroids C1 and C2. So here I'm fitting just 2 centroids or 2 clusters to the data. So maybe C1 is this data point that I just picked at random, and C2 is this other data point that I picked at random. These are going to serve as my initial cluster centroids. Okay, now I do step 1 of that kMeans algorithm. What I do here is to every data point, x of I, I'm going to assign it a cluster label. In order to do so, I'm going to compute the distances between xi and C1, so the distance between the particular data point I'm looking at and the first cluster centroid, and the distance between that same data point and the second cluster centroid. Whichever centroid is closest, that's the label I'm going to assign to this data point. So I'm going to set z sub I, again, the label associated with the data point x of I, to be 1 if the distance between x should be sub I here and the cluster centroid C1 is smaller than the distance to the other centroid. Otherwise, we'll give it the label 2 because the other cluster centroid was closest. So I took those randomly initialized clusters and now assigned data points cluster labels. Most typically for this distance measure, we're going to use the squared Euclidean distance. You could use other distances here, but this one is just computationally friendly and is kind of the gold standard choice here. The reason we use squared distance rather than standard Euclidean distance, which would have the square root on the outside here, is because they're going to give you the exact same cluster assignments, so save yourself a step of computation and you don't need to do the square root. Okay, so now that we have our first kind of round of cluster assignments, what we're going to do in step 2 is compute new centroids for each cluster. So in order to do this, I'm going to compute 2 new centroids, where the first is the mean of all of my red data points, so it's the mean of my red cluster, and I'm going to also compute the mean of my blue cluster. And the formula for doing that is down here. I just sum up all the data points in that particular cluster and divide by the total number of points in that cluster. If I do that, I get 2 new cluster centroids. So this red dot is the new centroid for the red cluster, and this blue dot here is the new centroid for this blue cluster. And you can see visually these are kind of in the middle of those corresponding clusters. Okay, those are the 2 steps in the algorithm, and now I just iterate. So I assign labels, again, just based on what centroid is closest, and then I update the centroids, do it again, and my centroids move a little bit further from one another, do it again, and now these look pretty good, right? And essentially we just repeat these steps until convergence. And again, the way we check for convergence is when none of our cluster labels are changing anymore. So when every data point gets the same label in 2 iterations in a row, then we'll just stop because nothing's going to change. Okay, questions on kMeans? Yeah.
So in the first iteration, you're randomly selecting 2 data points, but then following iterations, they don't necessarily have to be data points, they're just after using the...
Yeah, exactly. So in the first iteration, well, we need some way of picking initial clusters. We could randomly pick them, but then they might be really far away from the data, so kind of a heuristic strategy is just pick 2 random data points. But afterwards, notice my new kind of centroid of the blue data points is out here in the middle of nowhere land, and so it's not going to be a new data point that gets assigned that centroid. So they are not going to be data points after the first iteration. Other questions? Okay, so let's go through some more properties of kMeans now that we have a pretty good idea of how the algorithm actually works. The first is that for every centroid or every cluster you have in your data, it's going to define essentially some partition of the data space, really similar to a decision boundary that we've seen so many times so far. And in fact, between any two clusters, there's going to be a linear boundary between essentially the spaces that get assigned particular cluster labels. So everyone in this blue region gets assigned a particular cluster label, and everyone in this red region gets assigned a different cluster label. And these boundaries, again, are going to be linear. And the way you can prove this is really, really similar to how you would prove for nearest centroids. In fact, it's exactly the same computation. So, very similar to nearest centroids, except we're kind of automatically discovering these labels. With any kind of machine learning algorithm, I think it's a really good idea to take a look at how these algorithms can fail on real data. These algorithms work great when they work great, but there's plenty of cases where they don't. So kind of the simplest way kMeans can fail on a data set is if you just choose the number of clusters to be different from the true number of clusters in the data. So in this top left figure, I have actually 3 clusters in my data, at least visually. Maybe I fit kMeans with 2 clusters instead of 3. And you can see, of course, as you might expect, it doesn't pick up on the right sort of structure here. This is not such a major problem because we can tune the number of clusters, and we'll see how to do that in a little bit, but just something to be aware of. One way that kMeans can kind of more catastrophically fail here is if you have what's called anisotropically distributed data. So big fancy word for saying my data is not scaled properly. So in this data set here, I didn't pre-process my data by scaling. So essentially my feature on the x-axis has a little bit smaller scale than my feature on the y-axis, so my blobs are kind of elongated. And if I fit kMeans to this data set, well, it totally fails, right? It doesn't capture these 3 different blobs. So if I want to fix this kind of problem, it's really important that you pre-process your data using either standard scaling or this min-max scaling that we introduced before. Another way your models can fail is if that your blobs have unequal variance. So in this case, we have kind of a small blob over here, a medium-sized blob out on the left, and a very large blob in the middle. And to us, visually, there's clearly 3 clusters here. But kMeans really struggles to pick up on this because, it's in some sense it's a distance-based algorithm, and it can't account for the fact that sort of the scale for each of these blobs is different sort of per cluster here. So this is a pretty tricky one to fix kMeans for. Next lecture, we'll see a way that we can actually overcome this. Interestingly, you might have blobs that have sort of the same variance, but different number of points in them. So these blobs are roughly spread out in equal amounts, but just have different data points. And here, kMeans actually works pretty well. So again, it's important to understand your data before kind of just blindly applying a clustering algorithm to it, because there's ways it can kind of fail unexpectedly. As we saw before, kMeans produces these linear, essentially boundaries between the clusters. And so if you have clusters where it doesn't make sense to draw a linear boundary between those, well, kMeans is just not going to work. So here we've got kind of 2 crescent moons within each other. And again, kMeans can only produce sort of linear boundaries between these 2 clusters, and there's no way to linearly separate these guys. So no matter how much scaling and sort of pre-processing you do here, kMeans is simply not going to work. Okay, so I briefly mentioned that kMeans is guaranteed to converge, and let's kind of formalize what exactly I mean by that. So first, we're going to introduce some notions regarding how you actually measure how well your clustering is fitting your data. So I showed you guys these slides last time, but I think I went through them a little too quickly, so we're going to recap here. So we can compute the squared distance between a centroid and a data point. So this is just how far away a data point is from the centroid. We've already seen this. But if we kind of look at a particular cluster now, we can compute the squared error for that particular cluster. And what I mean by that is that I look at all the data points, say in the first cluster, compute the distance between those data points and that cluster centroid, and sum them all up. So in other words, it's sort of the sum total of how far away each data point is in cluster K from that centroid. It's kind of a measure of how spread out that centroid is. The squared error then is then the sum of all of these squared errors per cluster. So for every cluster, I get a squared error, and I sum these all up. And the way we can kind of quantitatively measure how good our clustering is by this squared error number. So in other words, we're quantifying how good our clustering is by the total distance between each data point and its corresponding cluster centroid. And the kMeans algorithm is actually guaranteed to converge to a local minimum of this squared error metric. Okay, let's kind of walk through the logic of why this is true. So at each iteration of kMeans, either I've converged, in which case I do nothing, or we do this two-step procedure where I compute centroids and update assignments. But each of these two steps, you can show, actually is going to reduce the squared error. So at every step of kMeans, I reduce the squared error by at least some small amount, or it stays the same. What this means in particular is it's impossible to revisit an earlier clustering. So if I see a particular clustering at step t, at step t plus 1, t plus 2, I can never go back because it would increase the squared error. Note also there's only a finite number of possible clusterings because we have a finite data set and we have fixed the possible sort of cluster assignments. And so what this means is that in the worst case, our algorithm could check every single possible clustering assignment. And so in fact, our algorithm is going to be guaranteed to converge after a finite number of iterations here. However, this is only at least to a local minimum of the squared error. We are not guaranteed to find the overall global optimal clustering. So this is a really nice property of kMeans. We're at least guaranteed to converge after a few steps. We can also look at the time complexity of kMeans. So this is per iteration of fitting the model. Again, we have two steps here. The first is computing memberships given centroids. And in order to do this, we need to compute distances for all n of our training data points. Each of our data points is d-dimensional, and we're computing those distances to each of our k centroids. So our first step is O of n times d times k. And our second step, updating the centroids. Well, in order to do this, we need to compute a new centroid for every one of our k centroids. And in each of these, we're summing up n data points, i.e. all of our training data, each of which is d-dimensional. So updating our centroids is an operation on the order of n times d. Okay, so what this means is that per iteration of nearest centroids, our total time complexity is going to be linear in the size of the data set n, the number of features d, and the number of clusters k. So not too bad, but definitely not ideal if you're trying to, say, cluster 10 million data points or something like this. Of course, this is per iteration, and the number of iterations that you do is going to depend highly on your data set and, say, how you initialize these clusters. Okay, in the portion about squared error and convergence, I mentioned that you can actually get stuck in local minima of this squared error metric with kMeans. And in practice, what this means is that kMeans is very sensitive to how you initialize these clusters. So let's look at an example here where you have kind of bad initialization just by chance. So 3 of my cluster centroids at initialization, these black dots, are up in this top left cluster, and only 1 is down here. And what we see is that after iteration 2, my clustering improves a little bit, but after iteration 3, well, I've actually converged. So in some sense, my clustering gets stuck in a local minimum because I just can't update these centroids any further. So it decreases for just a single iteration here, but kind of gets stuck and can't separate out these 4 different clusters. If I had a different initialization, i.e. I started at iteration 1 with 4 different randomly selected data points, well then I might have found a clustering that actually could separate these 4 blobs. Again, kMeans is very sensitive to initialization because it can get stuck in these local minimum. So what I've done here is that on the x-axis, I've randomly initialized kMeans on this same data set 100 different times. And on the y-axis, I'm plotting the squared error of kMeans after convergence. And I've sorted them by their squared errors. And what you can see is that for a good portion of these, about, say, 25–30% of these, they get stuck in local minima where they can only converge to a clustering that is, pretty poor. So these guys all have very high squared error. A good portion of the time, though, it is able to find a pretty good clustering with low squared error. So in practice, what you can do to avoid this local minimum problem is that there's kind of various strategies and heuristics here. The first is to just have a better strategy for initializing those first clusters. So what we've been talking about so far is just randomly picking data points, but there's, of course, smarter ways to do this. One of those is called kMeans++, and in fact, you'll be implementing this in homework 5. So better initializations definitely helps out a ton. Another thing you can do is, if you've got enough computational power, is just run your kMeans algorithm multiple times with multiple different initializations and select the one that gives you the best squared error. So again, there's tricks for getting around this local minimum problem. One thing I'll point out here is that actually finding the centroids and cluster assignments that achieves the global minimum of the squared error is an NP hard problem. So for all intents and purposes, it's impossible for us to actually compute this. And we really have no guarantee of finding global optima for this problem. For instance, one thing you could do, because there's only a finite number of clustering assignments, is just iterate over all of them, right? But there's something like on the order of k to the n possible clusterings if you're assigning n data points into k clusters. So for a tiny, tiny problem, where we have 4 clusters and only 100 data points, this has over 10 to the 60 possible clusterings that we would have to search over if we want to do sort of an exhaustive search for clustering. So in some sense, kMeans is like a heuristic kind of local search for this minimum. Okay, so sklearn, of course, has kMeans implemented in it, and you'll be exploring that in homework 5 a little bit. I'll point out here the important hyperparameters of this model. The first is initialization. So random is the strategy we've been talking about, where you initialize your clusters by just randomly picking data points. There's also kMeans++, which we kind of skipped the details of, but generally kMeans++ is going to work a lot better than random. There's ninit here, and what this is the number of times you're going to refit your kMeans algorithm in order to essentially get more randomization in those initializations. And then whichever one performs the best, as we said, we're going to use as our final model. Another trick you can do with kMeans is that, sort of as we said previously, each iteration of kMeans scales linearly with the number of training data points that you have. So if you have a huge data set that you're trying to cluster, kMeans might just be computationally infeasible to actually fit. So there's a trick here called mini-batch kMeans, where the idea is that at each iteration of kMeans, rather than computing the cluster assignments and centroids for every single data point, what we're going to do is we're going to take a subset of our data, randomly selected, and then update our centroids based on that randomly selected subset. So this is really similar to that stochastic gradient descent algorithm that we have seen before. And so it's just a computational trick that helps get some speed up here. Okay, you might also be wondering, how do we do hyperparameter selection for unsupervised learning? And really the main hyperparameter in kMeans is how many clusters should we choose? In practice, this is actually a quite hard problem, because we don't have any sort of ground truth labels. We don't know what the right clustering assignment here is. So we can't really create a validation set where we kind of know the answers and can evaluate our models on. So in practice, again, hyperparameter selection for unsupervised learning is very difficult. A cool property of KNN is that the squared error actually is going to decrease monotonically with the number of clusters. So if I increase the number of clusters, my squared error is going to go down. So that's exactly the phenomenon you're seeing here, where on the x-axis I have the number of clusters, k, and on the y-axis I have the squared error. What you can see is that as I increase the number of clusters from 2 to 3 to 4, I get a pretty sharp increase in this squared error. So adding more clusters is really helping me in terms of that metric. But after 4 clusters, well, my squared error doesn't decrease all that much. So in some sense, the optimal value of k here, the number of clusters, is something like 4, because we're not really seeing any improvement after 4, and if we increase much beyond 4, we're essentially going to be memorizing or overfitting the data. So maybe let me ask a question to you guys. What would happen if I made k extremely large here? What error rate should I expect to get? Yeah. Yeah, so 0. Why should it be 0? Yeah, exactly. So in the extreme case here, if we make k equal to the number of data points, we're going to get the 0 clustering error because, well, every data point is just its own cluster at that point. So in some sense, we still have this overfitting, underfitting trade-off. It's just much harder to evaluate because we don't have labeled data anymore. Okay, so any questions on properties of kMeans? Yeah. Yeah, exactly. So you might do 2 or 3 iterations, but then your cluster centroids kind of get stuck because when you try to update them again, your algorithm says, okay, no, I shouldn't change anything. All my data points are assigned in the right clusters. So it can get sort of stuck in some sense. Yeah. Yeah, so you're right that the squared error is going to be kind of noisy, right? Like if we run multiple initializations, we might get different values for the squared error in the plot like this. What you should do in practice is that for every value of k here, say k equals 2, run a whole bunch of initializations and take the one with the smallest squared error. It's not guaranteed to be the global minimum of the squared error, but if you try enough initializations, should be a pretty good estimate. Okay, other questions? Okay, so to wrap up today, we're going to see an example of what you can do with kMeans beyond just finding blobs in your data sets. And in fact, what we're going to do is data compression. So here we're looking at sort of this notion of lossy data compression, where the idea is you have some high-dimensional data that takes up a lot of storage on your hard drive, and you like to represent this data with a smaller amount of space, i.e. less bits. So, this is useful because it requires less memory, less bandwidth to transmit, but it comes at the cost of kind of reducing the quality of your original data. So I'm sure you guys are all familiar with like JPEG and MPEG, where you take an image, squeeze it down to a smaller file size, but looks a little bit worse. And in practice, compression algorithms and clustering algorithms have a lot of similarities to them. So I don't think people really use kMeans for data compression. These JPEG and MPEG are really the standards here. But kMeans is at least one way you could do data compression. So let's say we've got some original image, some color image with 3 channels, RGB, something like 400 by 600 pixels. And every pixel here, because it is a color value, is represented by 24 bits. So we've got 3 integers, one for red, one for green, one for blue. And essentially the intensity of those color values is represented by an integer between 0 and 255. So every pixel, we need 24 bits of information. We've got a pretty high dimensional image, so we need lots of bits to store this guy. And in fact, the total number of possible colors for an image of this size is something like 2 to the 24, so 16 million possible images we could have of this dimensionality. And the idea behind kMeans is that we're going to somehow take this color space, or pixel space, cluster it, and get a lower dimensional representation. Okay, so I took that image, and what I did now is I created a scatter plot of the RGB values in this image. So again, every RGB value is just some number between 0 and 255, so I can create a scatter plot of it. This is really a 3D scatter plot, and so I'm showing you these 2-dimensional projections. But what you should notice is if you look closely here, a lot of these pixels are quite close to each other in color. So we've got kind of like a blue blob up here, kind of white blob down here, orange blob down here. So the idea with kMeans clustering is we're going to cluster these pixels together, and instead of representing each pixel by its color value, we're going to represent it by its cluster label. So here's what happens when I quantize my color space by applying kMeans to it. What you can see is that, well, this patch now all has the same color value, this all has the same color value, this all has the same color value, so on and so forth. And in essence, what I've done is I've reduced the number of bits I need in order to encode these images. So if I use 16 clusters on pixel data with RGB values, well, all I need to do now in order to specify the color of each pixel is specify which cluster I'm in. So I only need actually 4 bits per pixel now. So if we do that, what we get from our original image is something that looks like this, where we've kind of grouped together very similar colors by doing this kMeans clustering. In fact, we've taken our 24-bit by pixel image and reduced it down to 4 bits per pixel. So 6 times smaller in terms of memory usage. Doesn't look great, so again, I don't really recommend you use this for your images, but this is a pretty cool idea of how you could use kMeans. If you increase the number of clusters up to 64, so higher value of k, you see you get a much better looking image because, well, we have more pixel values we can use to represent our images. However, this comes at the cost of, again, having a larger image that we need to store. Okay, let's go ahead and wrap up for the day. So this pretty much ends our discussion on kMeans clustering. Again, it's a very useful and simple clustering algorithm, really only 2 steps in this, where we find centroids and then assign their assignments in sort of a iterating fashion. We saw that this is guaranteed to converge to a minimum of the squared error, but again, only a local minimum. It's very sensitive to initializations. But there's various tricks for improving this that you guys will explore later on. In the next lecture, we're going to explore a topic called hierarchical clustering. There's a more advanced clustering algorithm that can kind of overcome a lot of the limitations of kMeans. And with that, we can end for the day. Thanks, guys.